So here we talk about the phasor. Actually, the concept of phasor is like, as much as we have sinusoidal stuff, sinusoidal input and sinusoidal output, actually we can just use a number to represent a sinusoidal function rather than writing the whole function. And actually we can use a complex number to represent a sinusoidal function with different amplitude and different phases, because there are two, just like for example, if it is like here, we have something like a cosine omega prime t plus phi. So there are two variables to determine this sinusoidal function. Yeah, we have omega and phi. Or likewise, we can here have another two variable to represent the same sinusoidal function, which is a C1 and C2 here. So if we just have different value of C1 and C2 multiplied by cosine and sine and then add them together, we can also form this different cosine. So actually we can just change it like C1 minus J or actually I. We change this to be a complex number, and then which can simplify our calculation. But let's see here, we have a resistor series with a alternating EMF. Rather than having a DC battery here, we have a alternating EMF, or it is a AC source. Sometimes usually we will call it AC source, which means that it is actually a sinusoidal. It is just like when you have a socket, like that one. We have AC power, we have AC source. So now we have AC source series with a resistor. So this AC source is like EM, which is the amplitude multiplied by cosine omega dt. So omega d is the angular frequency of the AC source. And as much as it is a resistor, so the resistor also have the potential difference. So I will write it like VR plus minus. So this should be like EM times cosine omega dt, because so this is E. So this one should be actually the same as E should be actually the same as VR. So these two are actually the same. And so the phasor. So here we define the term phasor of the alternating potential is VR. VR and IR are also the phasor, but VR is the phasor of the voltage, of the potential difference. So VR is actually a sinusoidal function, but we only try to use a complex number to represent this one. And we also, IR will be like EM over I cosine omega dt, something like this. We also would like to use a complex number to represent this current. And finally, the phasor itself will satisfy the Ohm's law. So this is nothing but the Ohm's law. And here we have a number times equals to a number times the resistor. So it will be easy. Rather than writing VR is actually a function of time equals R times IR of t. So this is actually a function of time. This is also a function of time. So actually this is still correct, but this is a function. So solving a function regarding to solving an equation regarding to a function will usually difficult than an equation regarding to some variables. And yeah, so as the case here, so we try to use a number to represent the function. So and it satisfies the Ohm's law here. So here we have VR equals to this one and IR equals to this one. Actually, we can just write, or actually we can write EM is actually VR. So we have a VR here rather than writing EM. But yeah, I don't think, So you can just consider EM to be VR, and it is fine. And here we will define that ZR is actually R. ZR is called the impedance, which is the complex generalization of the resistance. So in Chinese it is called 阻抗. And of course resistance is a 电阻. So in general, Z will be R plus JX. So we have impedance, resistance, and I forgot this one. What is it called? But here we have ZR equals R, which is quite trivial. So you may not know why do we need phasor. So let's see another case, which is the capacitive flow. So now we have still an alternating AC source here, which is series with a capacitor, So as much as we know E to be this EM times cosine omega dt, so VC will be VC cosine omega dt. And actually these two should still be the same. EM should be VC. And as much as we know IC should be dVC dt. IC should be C dVC dt, which means that we can just plug in this here and then take the derivative. So we have a CVC and then take the derivative, which becomes minus sine omega dt. And then chain rule, we also need to multiply by omega d. So finally we have omega d CVC sine of omega dt. And of course we have this is cosine and this is sine. So we can try to shift this sinusoidal function. So then we still have cosine here, but and actually as much as we have minus sign here and then with this sine, so it becomes cosine omega dt plus pi over 2 because this is a minus sine omega dt. And it makes this term to be positive. So here we will define the impedance of the capacitor to be 1 over omega c, because we hope to have this is VC, which is the which is the phasor of the voltage, and this is actually the phasor. This is actually the phasor of the of the current, which is something like this is like equals the real part of Vc exponential to j omega dt. Of course, here j is square root of -1, and here it will be equals to real part of omega d cvc exponential to j omega d t plus pi over 2. So we will say this is a real part of omega d cvc exponential to j minus pi over 2 exponential to j omega dt. So we will consider this part to be the Vc will be Vc, Vc will be Vc, and actually Ic will be omega d cvc exponential to j pi over 2. And actually j exponential to j pi 2 is nothing but j, so this is j, so this is actually j omega d cvc. So impedance of Z is nothing but Vz over Ic. So we have Vc over j omega d cvc. So Vc and Vc will cancel. It becomes 1 over j omega dc. And of course, we just write omega d to be omega. So we have 1 over j omega c here. In this case, if we use the phasor notation, this is the phasor of the voltage. This phasor will represent this trigonometry function or sinusoidal function according to the amplitude and the phase. The phase is 0, so this is a real number, Vc. This is the phase is pi over 2. So the phase is pi over 2 here, and then multiplied by the amplitude. So Ic is a complex number with the imaginary partner. Actually, it's just an pure imaginary number. And in that case, here it will somehow like satisfying the Ohm's law. So we have Vc, this is the phasor, equals Z times Ic, phasor of the current, phasor of the voltage, and this is the impedance. So this is somehow like the Ohm's law. So this is why we need to use the phasor. In this case, we can just use the complex number to represent the sinusoidal function of the voltage and the current, and the phasor itself will satisfy the Ohm's law, given the resistance is generalized to the complex impedance. So in this case, we will have the impedance of the capacitance to be 1 over j omega c. So its value depends not only on the capacitance, but also on the driving angular frequency omega d. Yeah, so it is related by this equation. So this is the case for the capacitive flow, and the other case for the inductive flow is like we still have the AC source here, and this is the inductor. So still we have E equals Em cosine omega dt. And yeah, for the inductor, we assume that IL to be IL cosine omega dt. And yeah, somehow independent to this one, First, we just assume that IL is Yeah, maybe you can just call it t prime, something like this. Not the derivative, but yeah, we already shift the time axis. So we assume the current of this circuit to be IL cosine omega dt. So it will satisfy VL. VL is the voltage difference or the potential difference across the inductor. So it is L dIL dt. So we can just plug in this here. So we have minus omega d IL sine omega dt. So just take the first derivative, and likewise we have minus sign here and then sine omega dt. We can change it to cosine omega dt plus pi over 2. And in that case, this is like real part of omega d L IL and then exponential to j pi over 2 exponential to j omega dt, something like this. So we will take this part to be the phasor, So in this case, we have the phasor IL to be IL, and then the phasor VL will be this one, will be omega d LIL and then exponential to j pi over 2. So which is like j omega d L IL. And in that case, we also use this definition. It still looks like the general case of the Ohm's law, V equals IR, but here we have the phasor of the phasor of the voltage, phasor of the current, and the impedance of the inductor. So ZL should be like VL phasor over IL phasor. So VL phasor is j omega d LIL. So we have j omega d LIL over IL is IL. So we have here j omega d L. And here we write it as ZL equals j omega d L. Or sometimes we only write it as a ZL equals a j omega L. So we will have ZL equals to j omega L, and then here ZZ equals 1 over j omega Z, and then the resistance is the simplest case, ZR is R. Yeah, actually I have rewritten the formula from the textbook, because when you just follow the textbook, it will be somehow not compatible with each other. So there will be some confliction between formulas and formulas. So I just rewrite it like this. So let's see a sample problem. Maybe you feel confused up to now. So let's see a sample problem here. So the resistance R, 200 ohm, and then the sinusoidal alternating EMF device operates EM, FD. And then what is the potential difference VR across the resistor as the function of time? What is the phasor VRT? So this is the simplest case. Even you don't care about the phasor, you can still make it right. So actually omega d is actually 2 pi FD, which is 120 pi radian per second. And of course VRT is actually 36.6 We have 36.0 here, and then cosine 120 pi t, and that's it. And so this is the time domain VR of t, and the phasor VR will be 36.0 volt. So this is the phasor. So this one is pretty easy. So yeah, and still we need to calculate IR. So IR of t is nothing but VR of t over R. So which is 36.0 over 200 ohm. And then cosine 120 pi t. So this is nothing but 0.180 cosine 120 pi t A. So this is the time domain function, and the phasor IR will be 0.180 A. So 31.3 is really easy. So let's see another one. So now we have the capacitor. The capacitance is 15.0 microfarad. So other will be the same, and so it asks you about what is the potential difference, Vc of t, and also the phasor, So in this case, Vc equals EM, which is 36.0 volt. So this is the phasor. And for the potential difference, it is still easy. 36.0 cosine 120 pi t volt. So this is still easy. And the next problem will be a bit different. So here we need to consider the current of the capacitor. The current of the capacitor. So now first we can consider IC to be J omega C Vc, or you can just go back to the original one. So we have Vc equals Zc times Ic, which means that Ic equals Vc over Zc, and Zc is 1 over J omega dC. So finally we have this expression, J omega dC Vc. So we have J omega d is 120 pi, and then C is 15 times 10 to minus 6, and then Vc is 36. So we will get J 0.203 A. So this is the phasor. And given the phasor like this, we will see that IC of t will be 0.203 cosine 120 pi t plus. So this is actually exponential to j pi over 2. So we have pi over 2 here. A. So this is the time domain function of the current. Of course, you can actually use I equals CD, IC equals CD, VC, DT. And then you plug in this function here, so that finally you will still get this one. But actually, we can just make use of the phasor so that we can simplify our calculation. For this one, you may not feel it is very simple, but as much as if we have a more complicated circuit, then making use of a phasor will be easier. Yeah, one thing I need to talk about is if you really write out the ODE governing the circuit, you really write out the ODE and then you try to plug in the initial value and then you find the complete solution, then probably you will find this is the particular solution. This is the particular solution. And we already just discussed the homogeneous solution. Homogeneous solution, we just ignore it here. Is ignore. Because suppose the circuit is stable, then the homogeneous solution will be something like exponential to minus alpha t times something. Sometimes it will be like exponential, only this exponential, but this is a negative exponent, which means that when t is large enough, this term will vanish. This term will tend to 0 as t is large enough. So that sometimes we only what we only concern is the particular solution, because this is a sinusoidal. The g of t, or the input here, is the sinusoidal function. So the particular solution is also a sinusoidal function. And yeah, and then it will goes to infinity for t. It will not decay with respect to time. It will just go from -1 to 1 and then go back to -1 and then so on and so forth. But for the homogeneous solution, it always will decay for the t when the t is large enough. So the phasor only concern the particular solution. I need to emphasize this here. Yeah, so let's take a look at another one, which is the inductor. So here, the inductor L is 230, and it is all the way the same. So now we need to find the phasor VL and also VL of t. So here, yeah, so here we have VL to be EM equals 36.0 volt, and VL of T is of course 36.0 cosine 120 pi T volt. So this is the phasor, this is the time domain function. So all the way the same as the previous two sample problem. So the next part, we need to find the current and the phasor. So for the IL, yeah, of course you can write it as a VL equals IL times ZL. And ZL is actually J omega DL. So this is ZL. So of course we can write it as a IL equals VL over J omega DL. And then we can just plug in the value 36.0. This is J. And then omega D is 120 pi, and then L is 230 times 10 to minus third power. So this is minus J times 0.415 A. So this is the phasor. This is the phasor. Yeah, and of course you can also write it as exponential to minus pi over 2 times 0.415, because J is actually this term. So in this case, IL of t will be 0.415 cosine omega t. Omega is 120 pi t, and then minus pi over 2 a. So this is the time domain function for the current. This is minus j. So if you still remember the Euler's equation, cosine theta plus j sine theta equals exponential to j theta. So if theta is pi over 2, then we have a cosine pi over 2. This is 0 plus j sine pi over 2. So this is j equals exponential to j pi over 2. So exponential j pi over 2 is j, and if so we have exponential to j pi over 2 equals j, or exponential to minus j pi over 2 equals to negative j. We have these two. Yeah, and of course the other one is, if you just plug in theta equals pi, we will have exponential to I pi plus 1 equals 0. This is another famous Euler's identity. So we combine E, which is the natural number, 2.718281828, and pi is 3.14 or something like that. And then I is the square root of minus 1. 1 is of course 1, and then 0. So we have all this number in one equation. Okay, now let's take a look at the general case. So here we have the series Llc circuit. So we have the AC source, RCL in series. Of course, you can just simply, like here, you can just write the second order ODE. So in, let's say here we have a second order ODE, and then you only need to add a source here, which means that in this case, on the right hand side, you have a sinusoidal source. So you need to solve for the particular solution for this equation to get the complete solution. But here, we only, we make use of the phasor so that we don't necessarily need to solve the second order ODE. But actually, we can still do the same procedure. So here we have RCL in series, and the current is given by this one, and the current I is given by this one. E will be like this. So here, this is the EMF, and then these are 3 elements in series, which means that the total impedance for the RLC will be by adding them together. In the textbook, it does not mention that the phasor of the L and C should be an imaginary number. So it will not be good. You do not know why we have R squared here, but we have this term here. But now I just tell you that the impedance should be R, ZR should be R, and then ZL should be J omega L, or omega DL, and then ZZ is 1 over J omega DZ. So when we just add them together, the real part will be R, and the imaginary number, this is J omega DL, so we have J omega DL. We have 1 over J omega DZ. So if we just multiply J on top and at the bottom, we will have minus J over omega DC. So we have this minus sign here. So in this case, the total impedance for this RLC is this one. And of course, we need to consider is that the V should be I times the total Z. So now V, the total V is nothing but EM. So in this case, the phasor I should be V over Z, which is like EM over let's say R plus J omega D L minus 1 over omega D C, something like this. So this is the amplitude, this is the original phasor. So there are some difference between them. We actually need to, so I is actually take the absolute value of the phasor. So this is a real number. So taking the absolute value, EM should be itself. Taking the absolute value of this complex number in the denominator, it will be like, so if you take the absolute value of alpha plus J beta, it will be like square root of alpha square plus beta square. If you take the absolute value. The absolute value is like, if you have alpha plus J beta, for example, this point is alpha plus J beta, which means that this is alpha, this is beta, And the absolute value is like, this is the absolute value, absolute value. The absolute value is like the length from the original point to that complex number is the absolute value. So it is square root of alpha square plus beta square. So in this case, taking the absolute value of this complex number is like R square plus this term to be square, omega D L minus 1 over omega D, quantity square, and then take the square root. So we have the amplitude to be like this. Of course, this is not so trivial, but yeah, but actually it's like this. So the next equation is like, maybe I will talk about the derivation tomorrow, but actually I will just finish this part. So rather than that, we not only need to get the amplitude, not only need to get the amplitude, but also we need to get the phase. So the phase is like, if we have similarly, if we have alpha plus J beta, the phase is like from here to here. So this is actually arctangent beta over alpha. This is the phase of this complex number. And actually, so we take the tangent phi here. But yeah, arctangent is not a very good expression, because if it is the other ray go to that side. For example, if you have alpha plus j beta here, and also we have minus alpha minus j beta, then arctangent this one and arctangent this one is actually the same, or it means that this is like theta, this is theta plus pi, and you know that tangent theta is actually the same as tangent theta plus pi, so we don't really know which one is whether it is this one or that one. So in that case, I just express it here like tangent phi. Tangent phi is actually this one. We also need to know the phase between this current and the voltage. It is not 0 plus or 90 degree anymore, as much as we have our LC in series. So we need to determine the phase difference between the voltage and the current. And actually, as you know, Z, I recall Z is EM over square root of R square, this is R plus J omega dl minus 1 over omega dc, like this. So this is a real number. So the phase of this one is 0. And the phase of this one is, of course, arctangent, this term over this term. So if you only consider, if you consider the phase of this one, the phase or actually the phase of I bar, the phasor I, then it should be like the negative. If you consider the phase of I bar, it should be minus arctangent omega dl minus 1 over omega dc over R with this minus sign. So we have this minus sign here. Because this term is in the denominator. But of course, as much as we have this minus sign independently, so we only consider tangent phi to be this term, to be the imaginary part over the real part, and this is the tangent of the phi. And one point here is that omega d here is 1 over square root of LC. This is not omega prime, not omega prime equals 1 over LC plus minus R over 2L squared. This is not that case here. Not that case here. For that case, it is like we don't have a source. And then the natural frequency of the Llc circuit is this term minus this term, and then take the square root. So it becomes smaller. But here, we drive this Llc circuit with this omega d. So the signal in this circuit will have the same frequency with the AC source. We have the same with the AC source. And here it talks about what is the condition of the resonance. Resonance. In Chinese it's called 共振. The condition for the resonance is that the imaginary part of Z to be 0, which is like imaginary part of Z to be 0. in this case, omega dl minus 1 over omega dc should be 0, which makes omega dl equals 1 over omega d. So omega d is 1 over square root of Lc. If this term is 0, then actually z will be a real number. Z will be a real number. Z will be a real number means the phase of the voltage and the current will have the same phase. And in that case, I will have the maximum amplitude because this term is 0. This term is 0 means the denominator take the minimum value. And the denominator take the minimum value means the whole term take the maximum value. This is why we call it the resonance and why it is meaningful. So in this case, we need to make sure that the imaginary part of the I to be 0, so that it satisfies the condition of resonance. And in that case, omega d is 1 over square root of Lc. Okay, so let's stop here today.